Uh, Welcome. As Annie mentioned, this is the second part of the webinar, a two-part webinar that we do on sign engineering, and it's to help project managers get a better feel for sign engineering, which should make them better project managers. As Annie mentioned, my name is Rob Alley. I'm an engineer with Elrod Engineering. And for those of y'all who are not familiar with Elrod Engineering, we've been providing sign design and structural engineering since the early 1980s and are proud to be members of MSSA. Appreciate you spending some time with us this morning. And over the next roughly 1 hour, what I want to do is give you what is hopefully going to be a helpful overview of what goes into the sign engineering for freestanding new and existing signs. Obviously, I'm not intending to make an engineer out of you, but in our experience, if you as a project manager have a good basic understanding of what goes into the design of a sign, you'll firstly have a smoother working relationship with your engineer. And then secondly, you'll be able to better serve your client, which is what we all want. We've got a lot to cover, and I'd love to have some time for questions at the end, so let's dive right in. In the first session 2 weeks ago, we spent some time on the general understanding of sign engineering, some of those fundamental underlying concepts, which we'll do a brief refresher on. But really, we're going to focus more on specific sign types, which in this case are freestanding signs. In the first webinar, we went over wall signs. So this time it'll be freestanding signs. Specifically, today we're going to cover freestanding signs after that intro, what makes a good sign order, and then the third part, which I think is particularly helpful and powerful, existing sign structure inspections. We get asked a lot about this, so I want to share some about that whole process. So the refresher on sign engineering concepts. The two main things we want to cover in the first part of this webinar today are the theory, basically what drives the design, and the practice. Theory being the building code, risk category, and exposure category and design loads. And then getting into the practice side, what kind of information is needed by your engineer and what makes a good project request. So the building code does a lot of things, but ultimately it tells us what and how loads are applied. City and state dependent, and so that can vary widely across a region. For example, in Texas, the default statewide building code in Texas is the IBC 2003 edition, and a number of cities have already adopted the 2021 version of the building code. So you've got an 18-year gap spread in those building codes. Other states have a state-specific building code. Common examples, North Carolina and Florida. North Carolina is more adopted by reference, and so it pretty much lines up with the current building code. Florida is pretty state-specific, as you would imagine, because of the high winds that Florida experiences. There are a few cities that have specific sign codes, but that's pretty uncommon. Chicago's actually phased theirs out. And then you've got some unique ones, which I get tickled about. Disney World has their own building code. It's called the Epcot building code. And that covers everything from signage, wayfinding, traditional signage, to roller coasters, castles, and other imaginative structures. So it's a lot of fun if you ever have a chance to look at that. So why does the building code matter to you in this range and spread of building codes? Basically, a sign that you build in one place may not be properly designed in a nearby city. A lot of times we see closely located cities. One of them will be the 2009 building code and another one will be the 2012. You would think, since those are sequential code editions, it would be a very similar, but they're very different approaches and they aren't necessarily compatible. Cities also do not view codes as backwardly compatible. So if you think, well, hey, we'll just be proactive and we'll do everything, have the engineer do everything to the 2021 International Building Code. if a city is set up for the 2018 or 2015, they will not accept a 2021 building code, even though the analytical portion of the code is identical. So there's no difference in the analysis that's done, but because it doesn't say the right code, they won't accept it. This is particularly important for clients with a pre-designed family of signs that are installed across a large region or even nationally. This is a building code comparison. Each building code references the specific American Society of Civil Engineers, or ASCE, design loads. So ASCE determines basically the mathematics of how a load is applied, and the building code references that. So as you can see, building code's roughly a 3-year cycle. ASCE is roughly a 5-year cycle. And so there is a little bit of coordination back and forth between that, but your engineers should be very familiar with all this. The two factors that I would argue have the most impact on design loads are the risk category and the exposure category. And so I want to dig into this just a little bit. The risk category, which is ranked 1 through 4, basically describes the use of a structure and how critical it is. Or if you put it another way, what are the consequences to human life in the event of a failure? The 3 exposure categories that essentially describe the surrounding topography, so where the structure or sign is located, and therefore how local wind loads are adjusted. It's weird, but I get a kick out of the fact that there used to be an exposure category A for dense, heavily built up urban areas. But once the engineering committee dug into it and started doing the analysis, they figured out it was too complicated to model. And so they just threw their hands up and said, either assume it's category B or do a wind tunnel study on your specific structure to determine those wind loads. This is a different layout for how these risk categories are arranged. Signage is generally considered risk category 1 or 2. Risk category 2 is the default level. And actually in the code, it even says if it's not 1, 3, or 4, it's considered risk category 2. Most people will consider and classify a small to medium-sized freestanding sign as risk category 1, though we have run into building departments and local codes departments that feel otherwise. Large freestanding signs or medium-sized ones located near crowded areas should probably be risk 2. And even though we're not focusing on signs that are attached to buildings, any sign attached to a building should be considered risk category 2 because that's the default for a building, unless the building itself is risk 3 or risk 4. And as you can see from this slide, risk category 3 is basically large assembly buildings. So schools, stadiums, sometimes convention centers or even theaters if they're very large. Risk category 4 is for critical infrastructure. So what about exposure categories? As mentioned before, the exposure category is basically a reflection of the topography surrounding a sign or a structure, and it's a measure of how rough the ground is. I'm going to summarize things for our presentation, but you can see from this slide the literal description of what we as the engineer has to consider in evaluating the risk category, the exposure category. Exposure category C is the default setting, open terrain with scattered structures. Exposure category B is more built up. As you build buildings, houses, whatever it is, that disrupts the flow of the wind and therefore creating turbulence, and therefore the wind load that is applied to a structure can be reduced. This is another example of exposure B. So you see, it's a pretty typical downtown area, not super dense, but representative of a lot of the downtowns in the South. And so this is exposure B. On the other side, exposure D actually increases the wind loads that are applied because there's less turbulence. Basically, exposure D conditions are on the edge of a large flat area, and extends downwind from the edge of that unobstructed area. Other than coastlands, it isn't terribly common, though we have seen times either in the Midwest, particularly just out in farmland in the Midwest, or along the Great Lakes, or along the Mississippi River, particularly around the New Orleans area where you have a long run of the Mississippi. Sometimes you can actually get exposure D on the banks of the Mississippi. One of the things I like to point out about this aerial photo of the Houston and Galveston areas that you can see all three exposure categories in this photo. On the right side, the lower right side, where you've got Goat Island, just the barrier islands there, those are unquestionably exposure D. You've got the Gulf, and then you've got the bay in here. So the buildings that are along the bay all of them will also be considered exposure D. As you look at downtown Houston, that's exposure B because it's a built up dense area. So the wind loads are less. And then just kind of the lower left corner, those are exposure C. So you've got all three categories here, which I think is just fun to visually see that. So now we get into the analysis. What are the specific loads that are going to be applied to a sign that your engineer will need to consider? These are all very creatively named. Engineers are known for our creativity. Dead load is quite simply the weight of the sign. Wind load, which is typically in the majority of the Mid-South region, wind load will typically control the design. It is a force that is applied to the sign due to the wind, which can push or pull or both. There are special wind regions, mainly out west in the Rocky Mountains, but in the Smoky Mountains, the Appalachian Mountains, you'll see that there are some special wind regions as well, which some special considerations need to be factored in for those wind regions. Snow loads, typically not a factor unless your sign cabinet is wide and you get a lot of snow, or if you're looking at a canopy. We talked about that a lot in the first webinar. So it can be significant in the South, which surprises a lot of people. Seismic loading is mainly California and Illinois, though there are a few other areas, particularly West Tennessee. And obviously seismic loading is due to earthquakes. So let's dig into freestanding signs. I'm going to give an overview of some different sign types, most of which are going to be familiar with you, and bring up some things that hopefully your engineer will be considering. Again, admittedly, we're only touching the surface, and I'm not going to try to make an engineer out of you, but I just want to open the window a little bit so that you can better understand some of these design factors that underlie the sign project, so that, again, I want to better that relationship with your engineer. First, let's talk about definitions. A lot of people use a lot of different names, and it's important to make sure that we're using words the same way so that we're communicating well. First, a freestanding sign is not connected to anything else other than the ground, of course. That's what differentiates it from a wall sign. Sounds obvious, but it's important to define it that way. Some different types of freestanding signs. Directional signs, these basically point the way for pedestrians or drivers, and are particularly useful when you're in a commercial complex. That is an important designation from a sign code point of view, as they a lot of times have different requirements, as you know, than another type of sign. So a monument sign is a ground sign with a low overall height, and it's solid to the ground. For the remaining two, pole sign and pylon signs, there's actually not a consistent agreement on the definitions, but for the purposes of this presentation, we'll go with the following definition. A pole sign is a freestanding sign with a visible support structure. A pylon sign is a freestanding sign where the support structure is enclosed by pole cover. So that's kind of the trigger. If it's got a pole cover, you've got a pylon sign. If it's got exposed poles, you've got a pole sign. This is a directional sign from a Starbucks that we did a few years ago. seems kind of silly, honestly, at 3 foot 10 inches tall to need this to be engineered. But the city required it because this was going to be installed in a hurricane area in Florida. And it was a real concern that at 175 miles an hour, this thing might blow away. So it was required. It's actually not the smallest sign that we've had to engineer, but this is, again, typical directional sign. And so just be aware that when you're working in high wind areas, city may require that this stuff be engineered. Typical monument sign. This is a graphic that we received from our client. A few questions that come to mind and should come to mind to your engineer. Is that base that's depicted, is that actually CMU block and solid masonry? Or is that some kind of a veneer applied to a frame? In this case, it was a CMU block base. And so that actually factors into designing the foundation. In this particular case, they show a round pier foundation with a concrete pad, and that's really not the most efficient foundation for this. You need a spread footer, you need a thick pad because just the sheer weight of the CMU block for that 5.5 feet. That pad, the support is going to be big enough that you're better off just doing a spread footer rather than having to do a round pier with it as well. This is another one of a monument sign that I like to show because it presents an interesting challenge a lot of people don't consider. As you can see in that upper picture, well, in all three of the pictures, 3 of the 4 pictures, the support pole for the sign cabinet is installed with anchor bolts, the J bolts, into the concrete block foundation. It seems like a good idea. It makes a lot of sense, except for one thing. In this case, all 4 of those bolts, the embedded anchors, are in the same CMU block cell. And per the building code, you cannot install that way. You can only install 1 J bolt or anchor bolt per cell of your CMU block. So this suggested design doesn't work. What we instead came up with was a short stub from the top of the foundation to the top of the CMU block base, and then the cabinet pipe was connected to it with a match plate. Problem solved. But your engineer needs to know that, because if you were to go out and install this and it got inspected and the inspector knows the building code, they would reject this because that is not per building code. So this is an example of a freestanding sign with a visible support structure. So it would be a pole sign. In this case, our client is looking at adding a cabinet to the existing structure. We'll talk about this more in a bit, but one thing that the engineer needs to evaluate is how is the loading changing by going from the existing cabinet to the new one. Other design issues to consider for pole signs. Things like the length of the pole stages. Will that be a transportation issue? Will it be an availability issue? We're getting more and more questions from clients that we spec out a certain size pole and you just can't get it. And so alternate sizes, alternate steel material, alternate diameters, wall thicknesses, all that stuff. Availability is, as y'all know, it's a big issue right now. Other factors, what type of foundation can or will you use? Can you do a round pier? Can you do a spread footer? Do you have to do a lateral wall? And how will the cabinet mount to the pole? That's particularly something that your engineer should know, because if it's going to be a cabinet that saddle mounts, the upper stage of the pole needs to extend all the way up through the cabinet, obviously, and they need to factor that into the design. Or if it's going to be a match plate and a mounting plate, that match and mounting plate need to be designed as well. This is another pylon sign because it's a freestanding sign with an enclosed support structure. Most people don't think about the fact that 19 feet wide pole cover would constitute a pole cover, but this is technically what it is. Some people would call this a monolith. Some people would call it a monument sign, even though it's 30 feet tall. different names for it, but technically this would meet the definition of a pylon sign. Of particular concern for this sign was the cabinet framing. You know, as you can imagine, it almost 20 feet wide by 30 feet tall, that's a big frame. This is actually large enough that you might either want or need to verify that the frame itself is properly designed. But if it's not, if the framing isn't required to be engineered, this is a pretty simple design to address. Just a pole direct embedded into a foundation. This is another freestanding sign that we did, and architecturally, this looks great. It was a fun project. Loved seeing it come out of the ground and getting photographs of it. But there are actually some issues that had to be considered with how the load from that center sign, that souk, how it transfers through the vertical supports on the sides. In this particular case, about 85% of the load of the sign goes through that innermost vertical pole. That may be an issue for the look of the sign. If this is probably heavily involved with an architectural team, and so the look, the visual look was so important that if that inner pole on both sides was larger diameter than the middle or the outer ones, that could have been an issue for the architects. So again, engineer just needs to know it, factor it in, and those kind of things need to be communicated with the design team to make sure everybody's on board with it. In this case, all the poles were the same diameter and everybody was happy. Or what about this freestanding sign? As shown by this structure that we engineered in Detroit, the possibilities of a freestanding sign are endless and can be very complicated architectural elements. We actually prepared the framing drawings for this, and it turned out to be a very complicated 3D structure where each frame section on the inside supporting the skin was different and required details and cut sheets for all those sections. It's a lot of fun. So we've talked about some examples of freestanding signs. Now let's get a little bit further into how loads are applied. This figure depicts both dead load and wind load. So as you can see on the left, the dead load, which is the weight of the structure, is vertical. It's just going straight down, pulled by gravity towards the ground. Wind load is shown on the right side. And as you can see, it is moving side to side. So it's trying to overturn the sign. So that pressure is being put on the side, and that's what's trying to overturn it. It's trying to rotate about the ground. This is a depiction of seismic loading. As you can see from this diagram, the actual analysis for seismic loading is pretty complicated, but it still might be necessary. Your engineer will analyze the structure and determine the seismic loading and compare that to the wind loading. Whichever is larger is what controls the design. And again, as I mentioned, we don't really think about seismic being an issue in the Mid-South region, but just as a reminder, West Tennessee and Memphis is, if you look at seismic maps, it is considered the most potentially active area of the country, much more active than along the San Andreas Fault and along the West Coast in view of damage that can be done. So when an earthquake hits Memphis or the West Tennessee area, it has the potential to do more damage than the ones out in California because of that seismic zone. So a lot of building codes in West Tennessee cities do have to evaluate seismic loading. So let's talk about foundation types. Again, terminology is important. You're familiar with all these, but just to lay some common groundwork. Round pier, some people refer to this as a caisson foundation. Technically, a round pier is different from a caisson. A caisson foundation is constructed at the surface and is sunk to the desired depth, as opposed to a round pier foundation, which is augured out. You may put in a rebar cage, you may not, you may just insert the pole and then you pour concrete. So again, slight difference, but technically caisson and round pier are different. A spread footing is basically a large block of concrete laid on its side in the ground whereas a lateral wall foundation is basically a block standing upright on its edge. Spread footings get applied for all different types of signs. Lateral walls, usually we only see those for monument signs, even though you could do it for a pole sign or a pylon sign if you wanted to. Let's look at some types of foundations. This is a round pier foundation with direct embedded poles. This is about as simple as it gets. As I mentioned, the poles are directly embedded down in the foundation. This seems to be the #1 choice for sites in Texas. With a lot of Texas companies, they have never done a spread footer and it's just unfamiliar, and you've got so much clearance above bedrock in Texas. This is what everybody loves to do. They like them big, they like them deep. This is another example of a round pier foundation, but in this case, you've got a cage of rebar inside the foundation. Typically, use this when either you're not wanting to have the support pole be directly embedded into the foundation, particularly if it's a deep foundation, that may just be wasted steel. And goodness, with the price of steel poles these days, it may be more cost effective to do a rebar cage instead of having 20 or even 30 feet of pole buried into the ground. Or sometimes either you as a sign company or the client just prefers to have anchor bolts, and that is totally legit. Maybe the pole might be relocated so they could be reused at another site in the future, or this is just the preferred technique from the sign company. This is an example of a spread footer. I like to show this example because typically an efficient spread footer design is longer in the direction of overturning than it is side to side. So if you look on the right of the diagram, you can see the side of the sign, and it's going to rotate left to right. That 7 foot 6 inch diameter, that is the direction of overturning. Normally, that's longer than if you look on the left and you see how wide it is. But in this case, because you've got the block foundation there at the bottom and that kind of planter type, or it's not really a planter, but that base covering, in this case, that had to be wider. So it's a little bit reverse than what you would normally expect, but those are things that need to be considered. This is an example of a typical lateral wall foundation. As mentioned, sometimes you might need a wide foundation for the concrete or masonry base, but you don't have the area for a spread footer. You go in and maybe it's a built up urban area, and you just, because of a parking lot, you're doing this in an island in a parking lot, you just don't literally have the clearance to do a spread footer, and you can't tear up the parking lot. So sometimes the lateral wall is the best application. Often these are installed with a backhoe just digging out a trench, and then you set the cage and pour the concrete, and then you go from there. So what about existing signs? We'll talk about this a little more in more detail in a minute, but this is a photograph of an actual sign that one of our clients sent to us and asked if the structure could be used for a new sign. There was no information about the foundations, no information about when it was installed, no information about the original cabinets. So there were a lot of questions and a lot of work needed to go into this. We were able to reverse engineer for what they could do. A good engineer can figure that out for you and help you solve your client's problems. So what is it about existing signs? This is a very powerful tool, but some things to know. According to the International Building Code for existing structures, a few important conditions. One is that the increase in loading has to be less than 10% from what was originally there. The second thing that has to be determined is the existing structure in good condition. And it's not a requirement of the building code, but it's really helpful if you can determine anything about the existing foundation. Sometimes you need to go into a sign structure actual inspection. In that case, getting dimensions of the existing sign cabinet, pole diameters, wall thicknesses, foundation, and what kind of condition everything is in. So we're going to come back to this in a few minutes, but this is just a teaser. What makes a good sign order? Refresher from those of you who attended the first webinar. The information that your engineer needs for a freestanding sign, the dimensions of the sign, height, cabinet dimensions. Are there any particular preferences that you've got for the pole? You may have something in your yard that you want to use, or availability may be limited. So you want to specify certain pole information. If there's something unusual about the cabinet, the weight is important. We do a lot of work for Cracker Barrel, and their cabinets, rather than, most of them have porcelain faces, and those are particularly heavy. So that's actually an added consideration we have to do when we're analyzing their sign structures. Do you prefer anchor bolts or direct embed? Do you have a preference for foundation? Not just whether you prefer to do round pier or spread footer, but there may be auger size that you're limited to if you want to do a round pier. You may be limited to 36 inch or 48 inch, or getting something exceptionally large may be so cost prohibitive that it's not worth doing. So that kind of information is good to know. Do you know anything about the risk category? You may not, but that's part of something that the engineer needs to know, and they can usually tell if you don't know. And then how will the cabinet be attached to the pole? Will it be a mounting plate or will it be saddle mounted? Some other information, are you going to be field welding or shop welding? Are there any transportation issues? Does the cabinet need to be in multiple pieces because it needs to be field assembled because it's too big? What kind of soil are you going into with a foundation? Is it undisturbed soil, or is this a new build site where they brought in backfill and may or may not have compacted it? It's particularly helpful when a geotechnical report is available, because that can give some good site-specific information. And then it's not critical, but groundwater elevation can also be helpful, particularly in coastal areas. That's something that may need to be addressed. So what about when a sign is already installed or manufactured? Any kind of survey photos that you've got and information you've got about it, the real dimensions, a lot of times they're fabrication details that is, as your engineer is trying to reverse engineer it, reverse design it, that kind of thing is very helpful. And then for, obviously not for freestanding signs, but if you have a wall sign, getting wall construction details is important information. So what makes a good order that you're going to send to your engineer? This is actually a snapshot from an order form that was developed for a client of ours who does a lot of repetitive program work. It comes in a spreadsheet, and all the different variations of this family of signs are included in the spreadsheet. And so the project manager completes this form with all the information that they've got, and then they put in the quantities of the different signs. This auto calculates what the cost is going to be, and then they just email it over to us, and that's how we get the job rolling. It's super clean, super efficient, and it works well when you've got a family of signs that are predefined that you're working from. That order form on the previous page is actually attached to an email like this. In this case, a couple things to point out. They've got a zip file there that's got artwork for the signs, the geotechnical report, building survey photos. One thing I like to point out in the middle is the street address for the sign. Surprisingly, a lot of times people don't send address information with a request, and your engineer is going to need to know that so they know which particular building code to apply to the site. Sometimes the street address is needed on the drawing because it doesn't happen often, but we have had times where a building or a sign department will not accept drawings for permitting if it doesn't have the specific street address, and then you have to go back and revise it if that's the case. So for contrast, what makes a bad sign order? We've gotten emails with no address for the site, no contact information for our client, no dimensions for the sign, just a graphic. And that makes it really hard to understand what we're going to try to engineer and do the analysis. Or slightly less difficult, but actually from my point of view, sometimes more fun. this is what we installed. The city is now requiring a permit. Can't you make it work out? We usually can. This is an example of a checklist. We'd be happy to send anybody that summarizes most of the information that your engineer would need. Obviously, you can't capture every situation on the form, but it does get most of it. Other things to keep in mind that aren't on here, undisturbed soil versus backfill, that is a big deal. And so need to know that kind of information. If your engineer doesn't get that information, they can usually make it work out, but the more you can pull together for them, the better. I know a lot of times you just need the engineering to pull your permits. And if you send the sign out to a local sub, they may not even actually look at the drawings for the actual install. But I wanted to point out a few things to note on drawings and calculations that might show why you would want to use these drawings and refer to them. So this drawing is for a pretty straightforward pole sign. And things to note here in the upper left corner, the diameter of the pole and the wall thickness, the thickness of the match plate, and the diameter and type of the bolts. In this case, A307's 7/8 inch diameter. Should be obvious, but again, you just want to check to make sure that you've got the right thing and you're installing it per the drawings. In the foundation, you can see there's little feet on the foundation. You can see the upper and lower rebar mat. You can see the depth of soil cover and the thickness of the foundation and the size and orientation of the rebar in the drawing. So in this case, the spread footer is actually square. And so you've got the same length of rebar in both directions. Typical analysis pages. A few things to point out. This is kind of, this is admittedly unique to the way Elrod puts together the analysis. Other engineers do it other ways, which is totally legit and totally fine. But so on the first page, the one on the left, you can see the diameter, the wall thickness that we used in our analysis. And by showing it 84.7% of its capacity, this thing's okay. A good rule of thumb for a new install is that you want to keep poles at less than 90% of their ultimate capacity. When you're analyzing existing poles, that number can go higher. But for a new install, you just want some built-in capacity there. If you look on the second page, again, a few things to note. This is an analysis where we've got the bolt diameter at that 7/8, number of bolts. You can see the number 60. That is the ultimate tensile strength for the A307 bolts. You can go to a higher bolt, A325 or A490, sometimes if you need to make that work. And then just the moment and loading. These are actually from two different parts of the calc, but the moment, the shear and the moment down there where it says 23.51 and 4.27, that refers to a different calculation sheet, but you want to make sure that those correlate correctly. Down below, we just use the spreadsheet so that they show green, obviously something works and meets code. If it were to ever be red, that means it doesn't. And hopefully you never get a sheet with red there, because that means I didn't proofread it well enough before I sealed it. The sheet on the left is from a foundation. That's for a spread footing. You can see in this case, it's 8 feet 3 inches by 8 feet 3 inches, 3 feet thick. Something to point out is if you look down towards the bottom, I didn't circle it, assumed allowable safe soil bearing pressure, 2.00 kips per square foot. And then the design safe soil bearing pressure, 2.0. Those are default values based on the building code. If you have a geotechnical study done on a site, sometimes you can get higher values, and that helps a lot. So that's important to remember. We check for overturning, we check for soil bearing pressure. Those are the two bolded values on that page. So again, I'm going kind of deep here for the analysis, but I've had several people say, hey, you send us calcs, can you tell us how to interpret it? These are kind of the things to look for to make sure it was done right. The next two shots on this slide are from the wind analysis that we do. I've circled in the middle one. Those are some dimensions of the sign and the wind load, and then it rolls onto the last slide, the one on the right, where we actually determine the pressure of 63.8 pounds per square foot. That's what gets applied to the sign itself. Just some information just to allow you to understand things better, what you're getting from, at least in this format, what you're getting from Elrod. Other people have different formats, which are totally fine. This is a sheet from a round pier foundation, different sign, different location, but I wanted to point out, again, up at the top, you've got the moment and the shear. Those are calculated from the loads that are applied to the cabinet and the pole. And then just down below that, the diameter of the footing and the depth of the footing. So those are where we determine the sizes of the foundation. And that value in the middle of the upper bubble, that 100 PSF per foot, that lateral bearing pressure, again, that is a minimum that you are allowed to use in the building code if you don't know what the soil type is. If you have a geotechnical study, sometimes that could be 150, 200, 250. That can significantly reduce the size of a foundation. So that's, if ever it's available, that's really important information to share with your engineer. It's also important to know 100 is the default that has to be used. Lately, we've seen a few that come to us for review that are defaulted to 150. That is not per code, and that is therefore not a valid design. So let's get back to existing sign structure inspections. What is the point of an existing sign structure inspection? Basically, nobody wants to get a call about this. Instead, this is what you want your client signs to look like. This photograph was sent to us from a sign company, excuse me, it was conducting surveys after an EF4 tornado hit Ringgold, Georgia a few years ago. One of the interesting things about this photograph is you can pretty much see every form of sign failure in the foreground and one very large sign in the back that didn't fail. I don't want to press this point too hard. A lot of times old signs that have been there for a long time, they didn't require engineering. And so they were just put up based on experience. But with codes changing, loads changing, wind speeds changing, just because something worked in the past or has stood up doesn't mean it's properly engineered, particularly when high wind events, whether they're tornadoes or derechos, that we seem to be seeing more and more of actually impact the signage. So seriously, what's the point? Three main things. Public safety, we all want to protect the public. Your client wants to prolong the asset life. And then I want to talk about, speaking from our experience, as to why these sign structure inspections are pretty important. Another thing, which is, I think, an interesting business opportunity for y'all, is that install a freestanding sign. That's a one-time project for your client, which can be a great project. But if you can get them to start doing inspections of their existing signs on a periodic basis, you can turn that into an ongoing revenue stream, serving the client well, making sure their asset stays up in the public health environment, and you develop a business relationship from a one-time event to an ongoing relationship. Public safety. Unfortunately, many large sign structures are located near the public, and this is just a nightmare scenario where you have a sign fail and it falls on a vehicle. Fortunately, the one on the right was unoccupied at the time, but it seems like every other year you do have injuries and fatalities that occur from sign failures. So nobody wants that to happen. The second point, prolonging the asset life for your client. As y'all know, a high-rise sign can represent a significant capital expenditure. I think we're seeing on some of the large interstate south style signs, I think we're seeing numbers just anecdotally from $500,000 to $750,000 for them. That's a huge expenditure for your clients. What is the average life of a high-rise sign? Nobody really knows. There's been some studies in that and nobody's come up with an answer. But if you could double the life of a sign, that would be a significant financial benefit to your client. And then thirdly, the case study example, just based on our experience with one of our clients. They've got about 700, 750 locations, and they asked us to review and analyze their sign failures in their program. They've had 4 failures. One was due to a tornado in Oklahoma City, in which the highest wind speed on earth was reported. The wind gauge broke at 305 miles an hour. So obviously you can't cost effectively design for an outlying event like that. Interestingly, the other 3 failures were due to installation issues. The mounting plates weren't fully welded to the pole. They were missing not just one, but missing multiple mounting plate bolts connecting the cabinet to the mounting plate. A good installation is critical to the life of a sign. And so working with good subs, making sure that your field crews that you send out do a good job, those are critical to having a good, strong, safe sign. And an inspection and repair program would have prevented 3 of those failures, the ones that were due to poor installation. So what are the primary components of a good sign inspection? Obviously, a detailed scope put together in advance, diagram of the structure, some of the details need to be diagrammed out. We found that a list of pictures is super important. It seems kind of overkill and over the top, but we've learned that because different people do different inspections, more consistency is better. And then we try to make it as easy to follow and as standardized as possible. On these next 2 slides, these are just some shots from the form that we use for an inspection. You can see the picture on the left, just kind of a summary of what needs to be done to give the field crew an idea of what they're going to be getting into. On the right, we always try to include a diagram, or particularly a photograph of the sign, and call out what needs to be measured as far as dimensions, wall thicknesses, circumferences, heights, lengths, things like that. The infamous photo page, like I said, exhaustive detail, but we've learned it's just a good reminder. If you've got somebody in a bucket 120 feet off the ground, they've got other things on their mind other than which particular photographs need to be taken. And so this form really helps to standardize that. On the right is an example of a detail of a splice and some of the measurements that need to be gotten and collected in the field, in addition to some condition evaluations that are part of that. A good existing sign structure inspection is done by a team of people. The sign company, a certified weld inspector, an engineer, and your client, all parts of the team. So what needs to be inspected? These are the different elements of a good quality structural inspection. And again, I just want to note, this structural inspection is different from a sign survey, much more involved, and shouldn't be confused with a typical survey. I'm going to give some examples of these and some types of things that we've seen just for reference. These are 2 cabinet photographs. The one on the left, you can see the top of the cabinet is, the skin is rusted out. And so anytime you have those openings that allows water to penetrate, and the more water that gets inside the cabinet, the more rust you're going to have. This is a secondary support member inside of a cabinet that had a lot of rusting. You can see in this case, you're actually getting section loss of that framing member. And so its strength is being significantly reduced and could become an issue for failure. Algae isn't necessarily bad, but it is indicative of water penetrating and staying inside the cabinet, and ultimately that will lead to rust. So this is kind of a secondary indicator of a potential problem in the future. This is a mounting plate. You can see the rusting on the plate is starting to degrade the meat of the metal there. And so this is something that is not a critical issue yet, but it needs to be addressed and needs to be taken care of before it becomes a bigger issue. This is a picture of a light arm where it attaches to the pole. A lot of times this gets overlooked, but you can see here, you've got rusting where the knife plate attaches to the pole, but of more concern to me is where the vertical and the horizontal light arm members go together. You've got the blistering paint, but it looks like you've also got rust that's penetrated all the way through the weld, or maybe it wasn't even a complete weld. And so you've got a pretty significant gap there that's greatly weakening this light support arm. The inspection program that we do for one of our clients actually started when a light arm fell off one night and landed in a parking lot. Fortunately, no one was below it, but that is kind of what triggered one of our big inspection programs. Here's some examples of splice welds. A couple things to note. On the left, this is really good notation because we're not in the field and y'all are, you're our eyes and ears. And so in this case, they noted everything very well. It's really hard if you look at that upper slot weld kind of in the middle. If somebody just sends us a picture of a slot weld and we don't have either a label or we don't even have its orientation on the pole, it's really hard. It's just hard to know where it is. And so this is some good notation. On the right, we see this, unfortunately, more than we should, but using a bolt to partially fill in a lift hole is not acceptable and does not seal up the hole properly. Another example of a splice weld, this was inside of a cabinet, and you can see a lot of that W2 weld underneath the rain cap is missing. Looks like the part in the middle may even be cracked, and so this is a very, very weak connection. Slot welds in the poles. In this case, there are no slot welds. They have the slots, they're open, and you can see that the inner compression ring from that next stage up pole is not connected to the lower pipe. Not only are there no slot welds in this one, but based on this photograph, it doesn't appear that there are even any inner compression rings, at least not lining up with the slots. And so that upper stage of the pole has way too much freedom of movement, and it's an insecure connection. Moving further down the pole, this is an anchor bolt, obviously an anchor bolt connection for a pipe. A few things to note. There needs to be grout underneath, and so it looks like a lot of that has worn out. Also, the anchor bolts need to penetrate at least 2 threads out of the bolts. So those, again, this is not a proper install, and so should have, had it been inspected, it would have failed the installation inspection. Another example of a base pole, this was actually partially buried underground. And interesting thing that happened, I think this particular case was from galvanic corrosion from the soil. You had enough of an electropotential differential between the soil and the pipe that the soil itself caused the pipe to be corroded. We've also seen it in cases where you have a landscaped area around a pole foundation and you've got a sprinkler there and it keeps it wet. And so right there at the soil interface, you get pitting. And in this particular case, it was significant enough that about 3/4 of the wall thickness had been eaten away. And then sometimes you just don't know what you're going to find. I've looked at this for years, and the one on the left, I can't tell what happened or how that happened, but it was not a pretty weld. And then the one on the right, that was interesting. There was a secondary sign cabinet that was installed to one of our clients' signs. An adjacent tenant was given permission to install a secondary sign cabinet after the fact of the first sign being installed. Obviously, this is not per our design or per acceptable design, but when they took the secondary cabinets off, this is what we found, and this quickly got changed. So once you've got all the data, you've collected it in the field, now what? We recommend having an engineer review, analyze, and make recommendations for repairs. Why have an engineer do that? It's frankly to give third-party objectivity. A client, you know, if you may have repairs of $30,000, $40,000, $50,000 or more that you're recommending to a sign structure. And if it comes from you, there could be some questioning of, is that really necessary? Because the sign company is going to be doing the work. And having an engineer involved with it, that just gives a little more objectivity because they don't receive any of those fees. They should seal the document itself. And so that just helps give your client comfort that the recommendations really do need to be done. And then one last thing to remember when you're out in the field, somebody's always watching. So in conclusion, hopefully this has explained a little bit about what engineering goes into your freestanding sign and what your engineer needs to know to give you a good design. It can be pretty straightforward, but there's also some complexity to it. If your engineer doesn't want to know this information, it may be time to reach out to someone else. And there are several very good sign engineers out there. I really appreciate your time.